Hey Ramblers, this video covers chapter 2.2 in our textbook, and it picks up where the video on chapter 2.1 left off. We're going to kind of review and reaffirm that what the meaning of the derivative is, or I'm sorry, what the meaning of the instantaneous rate of change is relative to the average rate of change. Then we're going to take a step further with that, and we're going to leave average rate of change behind a little bit as we start to work more with this instantaneous rate of change. And we'll see all the different names for the instant rate of change, the derivative, the slope of the curve, the slope of the tangent line. And I want you to become really conversant with that so that when I use one name for it, you're not confused. Okay, the last thing we'll do is we'll take a look at how do you find the derivative, as it's now going to be called, or this instantaneous rate of change algebraically. All right, so we'll look at an example of how to do that, and the exercises will give you plenty more work. So once again, take it slowly, pause often, take notes, and thanks for watching. Let's pick up in this video where we left off at the end of chapter 2.1, and that is this progression of the average rate of change of a function to the instantaneous rate of change, or what they're going to call the derivative. So the first calculation up here is the average rate of change. It's going from one point, a comma f of a, to a second point, a plus h comma f of a plus h. And you can see that this calculation is really just the slope. Now the denominator doesn't look like the change in x, but if you're careful to note that the change in x is moving from a to a plus h. So when you subtract the two x coordinates in the denominator, you'll end up with just plain old h. Alright, so what happens in this second calculation below it? Well, in the second calculation, most importantly, we take the limit. The limit as this distance on the x-axis called h, goes towards 0. So it's the same calculation as the average rate of change, but now we've taken the limit. Once we take that limit, we have a new term, and it's called the derivative. So the derivative equals f prime of x, and it is equal to the limit as h approaches 0 of f of a plus h minus f of a divided by h. Actually, I should say that this is really f prime of a. We will meet f prime of x a little bit later, but this is really the derivative at a point. So there's two names for what we're going to be studying. It's also to point out this term differentiable. Differentiable just means that a derivative exists. Okay, so let's take a look at some of the aliases that the derivative is known by. So let's see if we can erase some of this. Now let's zoom in here and take a look at this other exhibit. The derivative at a point A can be interpreted as the slope of the curve at A. So let's look at this, this graph on the right. What we're really interested in is, imagine this blue curve being the curve in question, and the tangent line is that line that just barely touches the blue curve. And what they're trying to show you here is that B was far away, and as it moved closer, these secant lines from A to B became the tangent line from A to B. That's what I did in the previous video, and I think the picture with motion was better than this diagram, figure 2.13. But again, back at figure 2.12 here, this is again the picture of the average rate of change. We're not going to spend much time on it now, but it's important to realize how the average rate of change evolved into the instantaneous rate of change. So the instantaneous rate of change will also be known as the slope of the curve at a point A, or the slope of the tangent line to the curve at A. All right, there's one more thing I want to cover in this video. I would like to show you how we calculate the derivative algebraically. So let's move on and take a look at that. Okay, the examples in this section are really good. So I would really like you to take some time to go through examples 2, 3, 4, and 5 on page 85. I'm sorry, just 2, 3, and 4 on page 85. Example number 6 was one I didn't think the book did a great job showing how to do it. So they're looking for the derivative. Now, once again, the derivative is the slope of the tangent line. And so in order to find that, we're going to need to use the difference quotient. And the difference quotient, these are all terms that you should make sure you get familiar with so that you're not confused when I use them interchangeably, as most mathematicians do. So difference quotient is going to be the limit as h approaches 0 of f of a plus h minus f of a all over h. Okay, well in this case, a equals 2. So f of x equals 1 over x, and a equals 2. So we're going to take the limit as h approaches 0 of 1 over 2 plus h minus 1 over 2 divided by h. Now again, why are we doing that? Well, since a is 2, we're plugging 2 in to the function, and the first term is going to be 2 plus h minus f of a. So here's 2 plus h, and there's the f of a. All right, when we work on that, if we were to try and use substitution, you would plug in 0, and you would get 1/2 minus 1/2 over 0, which would of course be 0 over 0. And that's our signal to do something. So one of the tricks I showed you at the end of chapter 1 was to get a common denominator. So I'm going to pause the video and I'll write all that step out. See if you can't do it on a piece of paper. Pause the video and do that as well. Okay, you can see that I multiplied both terms in the numerator by, well, I multiplied the left term by 2 over 2 and the right term by 2 plus h over 2 plus h in order to get the common denominator. That gave me a common denominator in the, that gave me a common denominator in the numerator of 2 times 2 plus h, and so my numerator became 2 minus 2 minus h, because I had to distribute that negative sign to both terms of that binomial. Okay, let's take a look at what that simplifies to. Okay, that becomes negative h in the numerator's numerator over 2 times the binomial 2 plus h, that's my total numerator, that fraction up in the numerator, all over h. Now if I simplify that, that means I have a fraction being divided by h. Well, that means I can flip the denominator, and it's like I am multiplying by 1 over h. And when I do that, the h's cancel, and I get the limit, of course the limit, I'm going to run out of room here. Okay, just to kind of bring us back to where we were at the end of that slide, the h's will cancel out, and I'm left with the limit as h approaches 0 of negative 1 over 2 times 2 plus h. Now I try plugging in again. So I try substitution again, and I get negative 1 over 2 times 2 plus 2, and I find that the value of the derivative is negative 1/4. Okay, that means that the slope of the tangent line at the point x equals 2 is negative 1/4. Well, let me quickly sketch that graph. So just relying on my parent functions, I did a quick sketch of that curve. And if I were to draw the tangent line at the point 2, at x equals 2, or in our case a equals 2, yeah, that would certainly be negative, and my sketch here isn't exact, of course, but I can believe that that's about a negative 1/4. Okay, so the derivative equals the slope of the tangent line. It equals this thing called the difference quotient. Um, you will find that there's many names for the derivative. All of them mean slope of the curve at a point. Okay, Ramblers, if this made sense, terrific, but otherwise go back, rewind it, take good notes, and I hope this helped.